All right, I'm going to talk about some complex analysis that's going to come up a bunch throughout the course. So here I'm going to say f is going to be a complex valued function, and going to write z as a complex number as x plus iy for xy real numbers. And f I'm going to write as having a real part u and an imaginary part v. So here u and v are functions from c to r. And I'm going to define f. I'm going to say f is holomorphic. So I'm defining holomorphic here. So f is holomorphic if and only if it satisfies the following partial differential equations. So du dx is dv dy, and du dy is minus dv dx. So it has to satisfy both of these. And the precise statement really is that f is holomorphic at a certain point if at that point it satisfies these partial differential equations. So these are called the Cauchy-Riemann equations. And let me give some intuition for what these mean. So I'm going to define this differential operator d dz bar to be, here I'm writing colon equal to mean I'm defining this. And then I'm going to put 1/2 here because that's what people do traditionally, but it doesn't matter for our purposes. So d dz bar is going to be defined to be ddx plus I ddy. And the point of doing this is that one can then say that f is holomorphic. And as shorthand for holomorphic, I write hollow and then m with an underline just because the word holomorphic is quite long. I don't want to be rewriting it all the time. So f is holomorphic if and only if df dz bar is 0. And again, the precise statement is that it's holomorphic at a point if blah blah, and is holomorphic on some set if it's holomorphic at every point in that set. So this d dz bar thing is really just unpacking the notation of the stuff above. So let me show you that, right? So d f d z bar by definition, well, I'm going to drop the 1/2, so maybe I'll just do 2 times this, is df dx plus I df dy, and then f was u plus iv, so this is du dx plus I dv dx, so that's the first term here, and then plus I times du dy plus I dv dy. And if this is, all of these 4 individual terms without the i's, they're all real. So we can just look at the real and imaginary parts of this expression here. And if we want this entire expression to be 0, both the real part and the imaginary part have to be 0. And from that, we recover the Cauchy-Riemann equations. And the reason to write it this way is because it gives some sort of very coarse, intuitive statement about what it means to be holomorphic. So f is holomorphic if it, and then I'm going to write it's only a function of z and not z bar. And this is, of course, like not something that can really be taken literally, but it sort of it gives the correct intuition. So, for example, whatever polynomial in Z, or rational function Z, if it didn't have poles, is going to be holomorphic. E to the Z is holomorphic. Log Z away from the pole is holomorphic. But the real part of Z, which you can write as Z plus Z bar over 2, is not holomorphic. And you can sort of see this from the expression, oh look, there's a Z bar, it depends on Z bar, it's not going to satisfy the Cauchy-Riemann equations. And of course, if you're unsure, you just check the Cauchy-Riemann equations. In practice, it's totally clear what is and is not holomorphic, and you just state, oh, this function is holomorphic, and there's very little checking involved. The reason why you can just tell by looking at something is because of the following fact. Is that holomorphicity is preserved under the 4 usual arithmetic operations, with a caveat that if you divide by 0, you are what's called meromorphic, which I'll define in a second. So you can't divide by 0 and preserve holomorphicity, but you're almost holomorphic. But more importantly, it's preserved under function composition. And this is the important one. So, if you look at, say, the log of a polynomial, that's also going to be holomorphic when away from the poles. So in practice, you can just tell by inspection that a function is holomorphic. So F is meromorphic. And then here we have to be a little bit more careful on some subset omega of the complex numbers. And here I'm going to restrict my attention to a specific kind of omega, and restricting it this much is not necessary, but it's going to save us some headaches for some of the stuff that comes later on in this lecture. So, and it's going to be enough for understanding the material for the rest of the course. So I'm going to assume that omega is compact with piecewise smooth boundary. And again, you can think of, these assumptions on omega are not necessary for the definition of meromorphicity necessarily, but I'm just going to take it to mean this here. So F is meromorphic on this set omega if it's holomorphic on that set, meaning holomorphic at every point, and I'm going to say except for some poles. And what I mean when I say except for some poles, if you want to have a sort of a more careful definition, I could say that there exists some non-zero polynomial such that if you multiply f by that polynomial, then the product is holomorphic on omega. But and that's tricky because you can have infinitely many poles and you're still you can still be meromorphic. So it's kind of a can of worms, and I just want to say except for some poles, and that's going to be enough for understanding what we do. And okay, so why do we care about holomorphic and meromorphic functions? I mean, they satisfy a lot of really nice properties, and the nicest property that they satisfy is that, so assuming that f is holomorphic on omega, and omega is going to satisfy these assumptions. So if f is holomorphic on omega, then the integral around the boundary of omega is necessarily 0. And this fact is very powerful, because if you're holomorphic on omega, you're also holomorphic on pretty much any subset of, not with these conditions, you're holomorphic on a lot of subsets of omega. And that lets you do some cool tricks. So, for example, this implies that the integral from some point A to some point B of f of z dz is independent of path, provided that you vary the path within omega in which f is holomorphic. And the proof of this is quite easy. So you've got some point A, you've got some point B, and you pick whatever random path, and you integrate along this path. Well, then you can also consider this integral from B to A, and then you've got this region omega inside, and if f is holomorphic on this region omega, then you know the integral around this boundary is 0. So that means that the integral from A to B this way is the same as the integral from A to B this way. So that sort of, this fact follows immediately from this fact. And another useful thing to know is that if you look at the integral around a circle, the real part of z is epsilon of 1 over z to the s dz, the value of this integral is 2 pi I if s is 1 and 0 otherwise. And for otherwise in the future I'm going to write OW, because otherwise is a long word to write. And the proof of this is quite easy. You can just parameterize this contour, and this will sort of pop right out. So what that means is that you can actually evaluate a lot of integrals around contours for meromorphic functions. So to do that, you can write f of z in terms of what's called a Laurent expansion. So this is basically like a Taylor series expansion. So this is going to be the sum n from minus k to infinity. K is some integer. I mean, it could even be 0 or negative, but just get to write it this way. And then it just looks exactly like a Taylor series expansion. So it's a Taylor series expansion around this point z naught, but you're allowed to have poles, right? These are the possible negative coefficients. So, or the terms in which n is negative. And using these two facts together, what you can say is, well, say f has a pole here, and you want to compute the integral along some path like this, some contour. What you can do is you can look at, so here's your pole, you can look at this integral that goes around, and then right before closing up, you take sort of this journey to the pole, you go around the pole in a circle, and then you sort of, here I'm writing these visually distinct, but you want to take the same path back, exactly following your tracks. And so that means that the integral along this line is going to cancel the integral along this line, just taking the same thing in the opposite direction. And the integral along this circle is going to be, well, what we just said up here, right? You're going to look at the Laurent expansion at this pole, and the only term in this Laurent expansion that's going to matter is the a minus 1 term. So this integral is 2 pi I times the a minus 1 at the pole, right? When you take the Laurent expansion at the pole. And then the integral, this big outside integral, this is the thing that you care about. And that gives you the, well, it's going to be minus this because you're sort of taking the contour in the other direction, which I guess I needed to specify the direction of this, but anyway. So that implies what's called Cauchy's residue theorem. So Cauchy's residue theorem is that if f is meromorphic on this omega, which I'm assuming is compact with piecewise smooth boundary, then the integral along the boundary of omega of f of z dz is equal to 2 pi I times the sum, and I'm going to write z in, or z naught in omega, but here, because f is meromorphic, somehow this is a discrete sum of the a minus 1 term of f so at each z naught in the domain, you look at the Laurent expansion, you look at the a minus 1 term, and you sum those up and you multiply by 2 pi, and that gives you the value of the integral along this contour. And this is a very powerful fact. So this quantity here has a name. It's denoted res at z equals z naught of f, and it's called the residue. Okay, so this is just a great way to evaluate integrals of meromorphic functions. So I'm going to give an example of how you would use this fact. So this is called Cauchy's residue theorem. Okay, so let me give an example of how you would evaluate an integral using Cauchy's residue theorem. And the example I'm going to give is maybe not the simplest example possible, but it's going to be very similar to a lot of stuff that we do later in the course. So I'm going to look at this integral 2023 minus I infinity to 2023 plus I infinity, so an integral along some vertical line of gamma function of z dz. And here, as a reminder, the gamma function at z is defined to be the integral from 0 to infinity of e to the minus x, x to the z dx over x. And this is a meromorphic function, and it has poles at the non-positive integers and nowhere else. And the residues are minus 1 to the n over n factorial. So here, the residue at minus 2 is minus 1 to the 2 over 2 factorial. And then another fact that we're going to use is Stirling's formula for the gamma function. So this is the statement that gamma of x plus iy absolute value is asymptotically, it's going to be y to the x minus half e to the minus pi over 2 y, and I think there's also a square root 2 pi here. Yeah. And this is called Stirling's formula. you may be familiar with a Stirling's formula, which is about approximating factorials. This is the same Stirling's formula, in fact. And this version is surprisingly hard to track down, so I will give a reference. This is in Gradstein-Rizek, Table of Integral Series and Products. So, I hope I'm spelling this right. Let me check very quickly. Yeah, Gradstein-Rizek, and then the equation number is 8 point. Let me also check this. 8.328.1. So here's a reference for this fact, and this is for fixed x as the imaginary part goes to infinity in absolute value. Okay, so after setting up these preliminaries, we can evaluate this integral. So the strategy for evaluating this integral is, okay, we've got this contour, so 2023, and then here I'm going to imagine minus it for some large t to 2023 plus it, and then we've got these poles. So it's 0, minus 1, minus 2, dot, and then, okay. And this is the integral that we care about along this line C1. And the strategy is going to be to take this contour, which is just this rectangle, and then we're going to thread the needle between two poles, and then we're going to close it up. So this is C2, it's going to be C3, and then C4. And Cauchy's residue theorem says that the integral along this whole rectangle of z dz is equal to 2 pi I times the sum of the residues. So I'm going to say this is going to be minus m. So it's going to be the sum n equals 0 to m of minus 1 to the n over n factorial. Because we had said previously that that's what the values of the residues were. You can look that up on Wikipedia, for example. It's well known. So we care about this integral along C1. So the strategy is going to be to say that the integrals along C2, C3, and C4 are all 0. And then we'll be able to just say this is the integral, the value of the integral along C1. So for the integral along C2 and the integral along C3, so the top and bottom segments, these go to 0 as t goes to infinity. And I'm not going to be careful about this because you can imagine that if n is really huge, then maybe these are very long, and so you got to be careful, but you can be careful, and we will be careful in the future when we're doing examples that we're a little bit more invested in. But for this, the idea is that you've got Stirling's formula, and that says that the gamma function decays exponentially as the imaginary part gets large. So along C2, you're integrating something that's exponentially small, and so if t goes to infinity, somehow you're gonna get 0 along this integral, and the same for the bottom integral. Then for the integral along C4, this one where we've sort of threaded the needle, this one goes to 0 as m goes to infinity, and the reason for that is that the residue at m is something like 1 over m factorial, right? So it's very small. So the value of the function here, in general, you can imagine is going to be very small. And again, you can be sort of more careful about this if you want to. You can use some recursion relation for the gamma to show that the value of the gamma function at this point is going to be something like 1 over m factorial. And so the integral along C4 is going to be small as long as you go between these two poles. If you hit a pole, of course, then it blows up. So don't do that. And so this integral along C4 is also 0. So what that means, these things together, is that, if we look at this, it's just that the integral along C1, which is the integral that we care about, of gamma z dz is equal to 2 pi I times the sum n equals 0 to m minus 1 to the n over n factorial. And I shouldn't write equals here. I should really write, tends to. As t and m go to infinity. And of course, this is just a series expansion for 1 over e. So we can say that the integral 2023 minus I infinity to 2023 plus I infinity of gamma of z dz is equal to 2 pi I over e. Okay. And this is something that we could have guessed, in fact. Let me explain how this is essentially automatic. This definition of gamma, the gamma of z, is the integral from 0 to infinity of e to the minus x to the z dx over x. This is a Mellin transform of the function e to the minus x. And this is essentially the definition of a Mellin transform, right? That if you replace e to the minus x with f of x, then that's, by definition, the Mellin transform of f. The Mellin transform is the Fourier transform or the Laplace transform under a change of variables. And just as the Fourier transform has an inverse transform, the Mellin transform also has an inverse transform. So the integral 2023 minus I infinity to 2023 plus I infinity of, now I'm going to write x to the minus z, gamma of z dz. This is the inverse Mellin transform of gamma of z at x. And well, okay, if this is gamma is the Mellin transform of e to the minus x, you can imagine that the inverse Mellin transform of gamma is going to be e to the minus x. So this is e to the minus x. And well, our integral was this, but here x was 1. So it makes sense that we're getting, sorry, the inverse Mellin transform has a 1 over 2 pi I here. My apologies. So if you just put in x equals 1 here, you're getting e to the minus 1 as the value of this, and then you get the 2 pi I because we didn't normalize it this way. So if we had just identified that this integral was, in fact, an inverse Mellin transform, then we wouldn't have had to calculate this using residues. We could just state, oh, it must be e to the minus x. But this is how you would use Cauchy's residue theorem to evaluate such an integral, and this sort of thing is something that we're going to do a lot throughout the course. It's going to be one of our primary tools of doing anything at all, really.